Welcome back to Astronomy. This is Chapter 5, Light and Matter, Reading Messages from the Cosmos, and this is the Part 6 video, Energy in Atoms. Before we consider energy in atoms, I want to think about something that's a little easier to relate to and to visualize. I want to consider the gravitational potential energy of a soccer ball. Remember that gravitational potential energy is related to the mass of the object, the strength of gravity, and the height that the object is, or another way to think about height is how far it has to fall. Now, if the soccer ball is on the ground, then it is at a height of 0, so we say it has 0 potential energy. But if we give it a kick, we impart some energy into it. Depending on how hard we kicked it, it will go up to a certain height. So let's say it's here at a medium height. We say then it has medium energy because the gravitational potential energy is related to its height. Now, if we gave it even more energy, a more powerful kick, we can kick it even higher and we give it more gravitational potential energy. I'm going to relate this to something analogous that goes on inside an atom. So instead of talking about a soccer ball and gravitational potential energy, we're going to look at electrons in an atom and their electric potential energy. Now here we have an illustration of a magnesium-24 atom. There are 12 protons and 12 neutrons in the nucleus, and there are 12 electrons going around it. And this is what's called the Bohr model of the atom. Niels Bohr was a Danish physicist. He won the Nobel Prize in 1922, and he came up with this model of an atom that has the nucleus at the center and the electrons going around in certain defined circular orbits. Now, we've since learned that they aren't exactly in those circular orbits, but the Bohr model still works pretty well, especially for illustration purposes and for thinking about many aspects of the atom. You notice that in this model of the atom, there are different levels that the electrons can be in. So the lowest level, kind of like the soccer ball being on the ground, we actually call this the ground state. So it's the lowest level, and we can say that it has the lowest amount of energy. Now you go up to the next highest state where the second level is, and we can call this level 2. We can also call it the first excited state, because if electrons are at a higher level than the ground state, they have an additional amount of energy, just like the soccer ball that was a bit higher up in the air. So we call this an excited state. And then there are other levels, and the higher we go, the more excited it is, the more energy it has. The analogy is to the soccer ball. The higher up the soccer ball is, the more energy it has. The electrons are the same way. The farther out from the nucleus they are, we can call that the higher they are, the more energy they have. One big difference between the soccer ball and the electrons is that with the soccer ball, it was referring to gravitational potential energy, the fact that there is a gravitational field and that the soccer ball has mass. That's what gives it its energy. Here, we're talking about electric potential energy. So this is related to the fact that there are electric charges between the electrons and the nucleus. Now, another big difference between the electrons and the soccer ball is that the soccer ball can be at any height. So it can be, let's say, 12 inches above the ground, or 13 inches, or 13.1 inches. So anywhere on that continuum, as long as you can kick it high enough, it can be at any height. But the electrons, they can only exist at certain heights. So they can exist at the ground state, or at level 1, or at level 2, and there can be level 3 or level 4. But the point is they can't exist somewhere in between. And these are what's called quantum levels. When you hear the word quantum, it usually has something to do with, well, quantum mechanics, which deals with these discrete layers or these discrete levels that the electrons can be at. It can either be here, or here, or here, but there is no in between. So here we have a ladder diagram. Now this specifically refers to hydrogen atoms, and we have these energy levels that are these numbers written to the right that apply to hydrogen. But if we ignore those numbers for a few minutes, the diagram and everything I'm about to explain on this slide works the same. So here we have the ground state. That was that closest circular orbit in the previous picture that electrons can be at. And then there's level 2, level 3, level 4, etc. Now, the levels actually get closer and closer to each other in terms of levels of energy. And eventually there's a highest level, and that's what's called the ionization level. As I mentioned in the previous slide with the Bohr model of the magnesium atom, electrons in atoms are restricted to particular energy levels. So an electron can exist at level 1, the ground state, or level 2, or level 3, or level 4, but there is no in between. So let's take an electron right here on the lower left at the ground state. And let's say we give it a little kick, just like kicking the soccer ball. So we give it a little bit of energy, and that energy can come from a photon or some other different methods, but we give it some energy. Now you notice, let's go over to the right-hand side. These are different energy levels. And I've taught you different units for energy, joules, calories. This is another unit of energy called the electron volt, so EV, electron volt. And the ground state has an energy level of 0 electron volts, just like the soccer ball sitting on the ground. The next orbit out, so the second orbit in those circular orbits, has an energy for a hydrogen atom of 10.2 electron volts. What that means is, if we want to kick it up from level 1 to level 2, we have to give it 10.2 electron volts. So if we have this electron in the ground state and we give it 5 electron volts, now that's not enough to make 10.2, just 5. If we do that to a soccer ball, we give a soccer ball a little kick and it'll go up and it'll go down, but an electron is very different. The electron will take that 5 electron volts, but it can't do anything with it. It's not going to jump up a little way and then fall down like a soccer ball. It will only react to an energy level, a specific energy level that will either kick it up to level 2, level 3, level 4, or a higher level. And so if you give it 5 electron volts, it won't react. It won't jump up. It'll just stay in that lower level. The 5 electron volts, perhaps it's a photon, it will just fly on through. It'll keep going. There will be no interaction. Now, interestingly, if you look at this second one, let's say we give it more than enough to go up to level 2. It needs 10.2 electron volts to go up to level 2, but let's say we give it 11 electron volts. It will not react to that either. So you might think that given an 11, well, that's more than enough to get to level 2, so maybe it'll kick it up to level 2, it only needed 10.2, and then it'll give you back some change. But it doesn't do that. It will not react to 11 electron volts because it will only react to the exact amount of energy that will kick it up to that next level, or a higher level than that. So let's look at the one in the middle. If it receives a photon of exactly 10.2 electron volts, then it will go up to level 2. If it receives 12.8 electron volts, then it will go up to level 4. Now, if it's on it can start at a higher level. Let's say it's at 11.2, and if you give it enough to go up to level 3. Now the difference between 10.2 electron volts and 12.1 electron volts is 1.9. So if from level 2 you give it 1.9 electron volts, then it will receive that energy and kick up to a higher level. Now in hydrogen atom, and all of these numbers on the right refer only to hydrogen atoms, and that'll become an important part, an important aspect to the next video, where we'll see that every atom has specific energy levels, but so these relate to hydrogen. If at any time you give it enough to be ionized, that means enough energy to be stripped away from the atom, it will just fly free. So if we started at the ground level and we give it 13.6 electron volts, it'll fly up, and that's enough to break it free. The analogy with the soccer ball is kicking it at such a speed, tens of thousands of miles per hour, so that it'll actually break free of Earth's gravity and go out into outer space and be gone. Well, that's what happens here. If you give it enough energy, so from the ground state, 13.6 electron volts, it'll go up and it'll just fly free. Now, you don't need a discrete amount. It can be 13.7, 13.8, it could be 15 or 20 electron volts. All you need is that 13.6, and then it's no longer bound to the rest of the atom. Now let's go to this one right here at level 2. It's already at level 2, so it's already up at 10.2 electron volts. To ionize it, it doesn't take as much energy. You don't need to give it 13.6 electron volts to ionize it because it already has 10.2. All it needs is to make up the difference. So to get from 10.2 to 13.6, all it needs is the difference, which is 3.4 electron volts. So it doesn't take that much to ionize it if it's already up there. Now, electrons can go up to higher energy levels. They can also fall down. So let's take an electron that's at level 2. If there's an opening in level 1, and what I mean by an opening is these different levels are allowed to have so many electrons. Level 1 is allowed to have, there are 2 spots where 2 electrons can possibly be. And the different levels have different spots that can be taken up. So if there is in a lower level an open spot, a vacancy, the electron will fall down to that vacancy. And this has to do with nature always going for the lowest energy state. The analogy with the soccer ball is if you've got a soccer ball up there in the air, it naturally will come down, the lower state being falling down to the ground. So electrons, if there is an opening, they will go down to fill that vacancy. So let's say we have an electron at level 2, and it will in very short time fall down. Now it'll fall down to level 1, and it just went from 10.2 electron volts to 0 electron volts. It just lost 10.2 electron volts of potential energy. So the question is, where did the energy go? Well, it gets released as a photon. And this is very crucial, as you'll see in the next video. That photon that gets given off, 10.2 electron volts, is a certain amount of energy. Now, as you've seen in a previous video in Chapter 5, a certain amount of energy is related to a frequency or a wavelength. So it gives off a certain frequency of light. We can detect that frequency of light, as I'll get more into in the next video, and it'll tell us that an electron or that electrons have fallen down from level 2 to level 1. Now let's say we have an electron up here at level 4. And let's say there's a bunch of vacancies in level 2 and level 3 and in level 1. All the levels below it, let's just assume there's some vacancies. This electron is going to fall down. Now, we cannot predict what level it's going to fall down to, only that, or what levels it's going to go, what steps it's going to take. We just know that if there is an open lower level, it will go down to it. So if there's a vacancy at level 1, it will eventually settle down there. But here's what it could do. It could fall down to level 3. And you can see the energy levels. It went from 12.8 to 12.1. The difference is 0.7 electron volts. And so it'll give off a 0.7 electron volts photon. And then it might fall down to level 2, giving off 1.9 electron volts. That's the difference between these two energy levels. And then it would fall down to level 1, giving off the 10.2. But there were some other ways it could have fallen down. Let's start it back up at level 4. It might just fall all the way down to level 1, thus giving off the 12.8 electron volts that it fell down. Or, let's start it back up again. It might fall down to level 2, so from 12.8 down to 10.2, the difference is 2.6 electron volts, so it would give off 2.6 electron volt photon, and then fall down, giving off the 10.2. So when it's up at a higher level, when there are many steps to go, we do not have the ability to predict what steps it's going to take. But what we do know is that when whatever steps it takes, it will release a photon that has a certain amount of energy that is equivalent to the amount of electric potential energy that it lost. Those photons that are given off are light that we can receive here on Earth, and so we can see what's happened. So all these different energy levels, the electrons can go in between them, and we call these energy level transitions. So it might transition from level 3 to level 2 or from level 1 to level 4. The only allowed changes in energy are those corresponding to a transition between energy levels. So in this picture, 1 and 2 are not allowed because it's not an amount of energy that brings it to another level. These two, in the middle and on the far right, those are allowed. Those are transitions that go between energy levels. And this one here is allowed as well. Now that's an extreme transition. This is an ionization, so it just got enough energy to kick it out of the atom. So what have we learned as we've gone through thinking about the structure of matter and the phases of matter? This actually goes back to the past couple of videos. Matter is made up of atoms, which consists of a nucleus of protons and neutrons surrounded by a cloud of electrons. What are the phases of matter? This was in the last video. Adding heat to a substance changes its phase by breaking chemical bonds. As temperature rises, a substance transforms from a solid to a liquid to a gas. Then the molecules can dissociate into atoms. Stripping of the electrons from atoms, which is called ionization, turns the substance into a plasma. And in this video, we've looked at how is energy stored in atoms. The energies of electrons in atoms correspond to particular energy levels. Atoms gain and lose energy only in amounts corresponding to particular changes in energy levels. The next video, part 7, is going to be learning from light. So we're going to take these concepts that we've learned throughout chapter 5, and we're going to apply them to why this matters to us in astronomy, how we learn about the things in outer space based on interpreting the light that we receive from them. So that'll be part 7. Have a great day.